Hello, my name is Valentin Vento, and in this presentation I will briefly talk about the research I've been doing with a professor at my previous university. The research is on determining physical properties of molten salts by using computational chemistry. In this presentation, I will talk about what molten salts are, why we use computational chemistry as a material characterization tool to determine thermophysical properties of molten salts, how computer simulations work, and I will also present how we determine the heat capacity of a specific molten salt. Molten salts are ionic compounds that are solid at room temperature but liquid at high temperatures. They are made of positive and negative ions. They have a high heat capacity, are thermally stable, and are good at transferring heat. If nuclear fuel, like uranium or thorium, is dissolved into molten salts, the molten salts can be used as coolants and fuel in nuclear reactors. Despite its potential, these are compounds that have never been studied, and this holds back the development of molten salt nuclear reactors. In order to develop the reactors, information about the thermophysical properties of molten salts must be determined, and that's what we are doing with the use of computational chemistry. Computational chemistry has several advantages over doing wet experimentation research. Computational experimentation is cheaper, faster, and as accurate as wet experimentation, which has to be done using expensive material and inside of a globot, which can be difficult and also dangerous. Ab initio molecular dynamics is a specific computational chemistry method that we use. AIMD allows us to simulate how atoms behave over time based on quantum mechanics. Here is how it works. We start with a simulation box, which is a cube with a fixed edge length. Inside this box, the simulation randomly places atoms to represent the molten salt. Then, using quantum calculations, it determines the energy of the system based on those atomic positions. Then, from the energy, the simulation can compute the forces acting on each atom, then the atom acceleration, velocity, and finally their net position. This process repeats step by step, simulating how the atoms behave over time. So in our research, we try to determine the heat capacity and coefficient of thermal expansion of the salts. In order to do this, we follow 4 steps. We first determine the number of atoms and the temperature for the simulation. Secondly, we do a series of simulations at different volumes to get a rough estimate of the equilibrated volume. These runs are called zoom-out runs. Then we narrow down the range around the rough estimate that we calculated in the zoom-out runs. We run 5 simulations to better estimate equilibrated volume. These runs are called zoom-in runs. And lastly, we use the equilibrated volume to run 5 simulations to measure the system's average energy. From these runs, we calculate the heat capacity and the coefficient of thermal expansion. So now that you have seen the steps that we use to determine heat capacity, let's walk through a specific example to see how it is applied in practice. In this case, we studied a molten salt fuel containing 1 molybdenum atom, which is a contaminant that can leach into the salt from the reactor chamber walls. We studied this salt at 11 different temperatures in the 773 Kelvin to the 1523 Kelvin range. So our first step is to determine the run parameters. This is the number and kind of atoms that we will put inside the box and the temperature. For this case, LIFAF MOF6 has 54 base salt atoms, 10 uranium atoms, 46 fluoride atoms, and 1 molybdenum atom, which makes a total of 111 atoms. Then, for the temperature, we select one of the temperatures that I presented in the previous slide. We have to do this for each temperature. The second step is the zoom-out run. Remember that the goal of this step is to get a rough estimate of the equilibrated volume, which is the volume at which the pressure is 1 bar. For this, we pick 9 edge lengths that are separated by 0.4 angstroms. We picked these edge lengths because from experience we know that the calibrated volume will fall within this range. So in this table we can see the 9 edge lengths that we picked. If we cube these edge lengths, we will obtain the volume, and these are the pressures that we got from the simulations at each of the edge lengths. We plot pressure versus volume graph and solve for the calibrated volume and the calibrated edge length. So in this case we determine that the rough estimate of the calibrated volume is 1672 cubic angstroms, which is a cube with an edge length of 11.87 angstroms. The fourth step is doing the zoom-in runs. The zoom-in runs are like the zoom-out runs, but they result in a better estimate of the calibrated volume, since we are zooming into the region at which the pressure is 1 bar. So in this table we can see that in this range of edge lengths, our midpoint is the rough estimate of the calibrated volume that we got in the zoom-out run. We generated 8 more edge lengths in increments and decrements of 7 angstroms. So we run these simulations 5 times and we get the average pressure of all 5 runs. We plot a graph of average pressure versus volume and solve for the volume at which the pressure is 1 bar. This is the calibrated volume, and this is the calibrated edge length. The last step is the heat capacity runs. For these runs, we use the calibrated edge length that we calculated in the zoom-in runs for each temperature. We run the heat capacity simulations 5 times and collect the energy that the atoms contain. In this table, we see the calibrated edge length of each temperature and the energy that the atoms contains in each repetition. This is the average energy. We obtain the heat capacity of the salt by plotting a graph of average energy versus temperature and determining the slope. So the slope in this case is 1.04 times 10 to the negative 3 hartrees. Converting this to joules over Kelvin and dividing it by the number of cations followed by conversion of molecules to grams via Avogadro's number and the molecular weight, we got that the heat capacity of LIFAF MOF6 is 0.676 joules over grams per kilogram.